design or underground opening, right? So that need to be designed in a software called RS2. Okay, but for learning purpose, we are going to, as I said, we are going to use this phase 2. This is, the same software this phase 2 is. And everybody will choose their own project, right? Like as I said, as we do it in our do-it-yourself DIY project. So if you cannot find a project, I'll definitely give it to you. And in next class, I'll be telling, I'll give you instruction how to solve this whole thing. Okay, so please don't worry. Yeah, so let me start with the previous example we were solving. Okay, so what I can see is you most of you have submitted the assignment, so I believe you understand, you know how to solve this problem, right? And anybody who could not do that. Anybody who could submit or who knows how it to be done, can you please put your hands up? Aniket Kumar Gupta, can you hear me? Anybody who, guys, can you hear me?
Yes, sir. Your voice broke a bit right now, so we couldn't hear what you said.
Okay, so what I was saying is, like we were discussing about a problem last class. So could you go through that problem? This is my question. And
Yes, sir.
anybody who has, doubt solving this problem. So can you please raise your hand who has solved this problem?
Sir, Aniket replied in chat, sir.
Okay. Yeah. Okay, only 14, 15. Okay, so we still have, I don't know, like whether you have submitted, you are listening to me or not listening, I don't know. Okay, let's quickly see this example problem. So it says at a depth of 750 meter or 10 meter diameter circular tunnel is driven in a rock having a unit weight of 26 kilonewton per meter cube. And Inertial compressive strength and tensile strength of rock is 80 MPa and 3 MPa respectively. Will the strength of the rock on the tunnel boundary be exceeded if K equal to 0.3 or K equal to 2? So as we discussed, we have this tunnel here. Okay, we have this tunnel at a depth of 750 meter, and we last class we discussed that okay, the most critical location where the principal stresses are vertical and horizontal are at this point and this point, and this you can find it out using the Course equation. Okay, so if you put this sigma theta equation and differentiate it d uh, sigma d sigma theta by d theta of this equation and put it equal to 0, so you can find out where are the values actually where you can get maximum or minimum. So is this like our derivative thing we were doing in our 10 plus 2? Okay, so then you can find out that okay, the most critical location in a tunnel where the principal stresses are vertical and horizontal are these two locations. Is this clear what I'm saying here?
Yes, sir.
Now it is asking, let's say we know from our vertical, the stresses, we can calculate it from our density and depth of our tunnel. So this is saying if the stress ratio, the horizontal to vertical stress ratio is 0.3 and 2, like is the rock strength good enough to take care of that load? So that is the question. Is this the font size is okay, or I need to zoom it a little bit? Can anybody tell me?
Zoom it a little bit.
This is can you see it now? Yeah, because I wanted to put both the screen actually.
Yes, sir, it's visible.
Okay. So first thing what we need to do is, like if you see the equations around the tunnel boundary, we said that, or maybe we discussed that the stresses in radial direction, which is sigma r equal to 0 at tunnel boundary. And anybody has a question about this, like why this sigma r equal to 0 at the tunnel boundary? Because nothing is there to give a stress or maybe to push it from inside. So the boundary, this direction perpendicular, like towards the radius, the stresses are 0. The only thing which we are worried about is the sigma theta theta. Okay, and we need to see how it is changing. So if you put, as I'm saying, first theta equal to 0, this is one of the critical location. So at theta equal to 0, this becomes, the equation becomes, if you put it in that course equation, sigma theta theta becomes P into 1 minus, 3 minus K. Okay, and at this is theta equal to 0 degree. And at theta equal to 90 degree, this becomes how much? Anybody who has solved?
Sir, P into 3K minus 1.
Yes, P into 3K minus 1. So now if you put these values, so if you put these values in or maybe you calculate the values. First thing is to sigma V. So sigma V equal to gamma Z, that is what 26 into 750. If you just multiply this becomes 19.5 MPa. Okay, so you need to remember something here. Okay, so when we have our this is our ground level, and we are talking about how the stresses are varying with the depth. Okay, so at 750 meter, we calculated that exactly at that location the stresses in vertical direction is 19.5 MPa. And when we are saying that K equal to, let's say, 0.2, so that means sigma H by sigma V equal to 0.2. So sigma H becomes 0.2 into 19.5. So this becomes how much? 5.85. Okay, and in the second case, K equal to 2, this becomes sigma H equal to 39 MPa. Now the important point to note here, so the first case, this in this direction the stresses, the vertical direction the stresses are
Excuse me,
19.5.
sir.
Yes.
Sir, it will be K is equal to 0.3, not 0.2.
Oh, 0.3, sorry. Thank you so much. Yeah, so if this is K equal to 0.3, this is 5.85 MPa. Then this is 5.85. So, but the thing is, we are saying that our tunnel is at a depth of 750 meters. So, this bottom of the tunnel goes 10 meters down, right? So, this is 10 meters, right? And what we need to do is, when we do this FEM analysis, or maybe even the cost equation, if you see that the cost equation says if a tunnel is excavated, circular tunnel is excavated, and these stresses are, let's say, P and K times P, then our equation valid. So what does this mean is, in this direction, from this point to this point, the stresses are uniform, and that is P times K or K times P. Do you think is it possible? Because let's say this is 10 meter, and this can be, like 50 meter, right? So what will be the stresses here? Will it be more than this vertical stress which is there in the top of this tunnel, or no? Or is this less? Let's say at point P, if I ask you at point A, what is my sigma V? Will it be more than 19.5, or will be less than 19.5, or equal to 19.5? What it will be like? Can anybody tell me? Anyone?
Sir, less.
Less than.
Yeah, because this is a little bit higher, right? So if you are doing that, gamma z will be less, right? So this point the stresses will be less, and this point the stresses will be more. Let's say this point, the bottom point is B. Okay, so for point A, the stresses will be less than 19.5, and point B, sigma B will be greater than 19.5. This is clear, right?
Yes, sir.
So now if this is there, then our equation itself is not valid, right? Like the cost equation we cannot even use. Okay. Right, because this is kind of a triangular distribution of stresses. So if you see this thing, it will be something like this. So at this point, the stresses are more, this point less, little bit less, and this is the least, the stress values, right? Similarly, if you see the stresses here in the boundary on the top, it will be less or more than the boundary at the bottom, like these stresses. This one and this one, let's say if you compare the at the top point, the stresses will be less, right? Yes or no? Please respond.
Yes, sir.
Okay, so do you think this Scott's equation is valid?
Sir, what?
The equation which we derive here, this one, or maybe we talk about here, do you think is valid? Anyone?
No, sir.
Yeah, so could you solve this problem then? How did you do that?
Sir, it will be approximately equal. So
What do you, can you just quickly calculate what is the, like, let's say this is 50 meter above this line. So what is this, this value? Gamma z equal to? So this is 700 now, right? Like 2600 into 700. What is this value? Anybody?
sir, 18.2 ampere.
18.2 ampere, right? So this is this is around 1.3 ampere less, and it will be 1.3 ampere more. Okay, so 1.3 ampere means 20.8. So this is 20.8, and this is 18.2. Okay, so in this case, maybe we can assume, right, that this is equal to 18 equal to 20 if you are okay with that, or maybe you just take the average value and apply the stresses all around. Okay, so this is what, because we don't have any other option. But this Scott's equation, let's say if you want to, apply for a depth of, let's say the tunnel is 50 meter deep. You cannot apply, you cannot apply Scott's equation. Is this clear? But if the depth is more in this range, we can assume that, okay, like this is changing little bit, like 18.2 to 20.8, but we are okay with that. Is this you got the point here?
Yes, sir.
Yeah, basically we take these assumptions when we do the modeling work, right? Similarly, quickly just tell when k equal to 2. So we have two conditions here. One is, k equal to 0.3. So that is 19.5 and 5.85. And we have second condition, this is 19.5 and 39 ampere. Okay, and if you put quickly the value, what are the boundary stresses, it will be coming here in this point and this point. For two cases, it will be just putting sigma theta theta equal to, at this point for this case, this will be 19.5 into 3 minus k into this equal to this k equal to 0.3, so this becomes 52.65 at theta equal to 0 degree. And if you put the value of sigma theta theta at this point 90 degree, so sigma theta theta equal to 19.5 into 3k minus 1, that becomes minus 1.95 MPa. Okay, so that theta equal to 90 degrees. Something important to see here, like that if we have a compressive boundary stresses, like what we are doing is, let's say, we have a plate, let's say steel plate, and we are applying some stresses from the all around, right? All around stresses. The stresses are compressive initially, but if you create something here, okay, this stress can go tensile. This negative means it is tensile stress. Okay, so this is why, like let's say if the shape is circular, then it is this. If it will be different shape, it will be different. If it is rectangular, it will be different. Okay, so this change in stress that happens depends upon what is the in situ stress that is coming and what is the shape of this excavation. Okay, this is clear. Even if the compressive stresses are there, it can generate some tensile stress based on your excavation. That's why this FEM modeling or the calculation of the stresses becomes very important when you design something. Is this clear?
Yes, sir.
Okay. Similarly, for k equal to, if you just put k equal to 2, the sigma theta equal to 19.5. I'm not solving it. You please do it yourself. At theta equal to 0 degree and sigma theta equal to 97.5 MPa. All values are in MPa, and this is theta equal to 90 degree. Okay, so today our task is to see using FEM, this finite element code, this phase 2, can we get these values or not? Okay, so that is our task. So let's learn this thing. Please please try to please try to understand what I'm saying here. If you have any question, please ask. Okay, otherwise, it will be it will be difficult for you to this solve your project. Let me take a break here.